Welcome to Spring LIB.
Our goal here is to find the magnetic field of a sheet of current that's made up of individual wires. For the sake of imagining them, they have a square cross-section, each carrying a current into the y direction. And what we'll need for this is Ampere's law. So we're assuming that the sheet is large enough that we can use some simple symmetry. But the Ampere's law says that the projection of B along a closed path is equal to mu naught times the enclosed current. And you almost never do the integral on the left-hand side. You use symmetry and choose a symmetrical path to take that projection along, which you are expecting the magnetic field to be uniform. So here we're going to use what we know about a single wire in order to figure out what our path should look like. Maybe I should draw that single wire with a cross-section that's a square. So it looks a little bit more like the situation we have. But just assume a simple wire. What we used with, yeah, this isn't going to work perfectly, but if you have a current going down a very long straight wire, what we know the magnetic field does is wrap in circles around that wire. And I'm just going to show them in a square sense. So using the right-hand rule, the magnetic field kind of wraps around in a square type situation. It really circles around wire, but because we have square wires here, what this is going to tell us, you can imagine two squares side by side. The side magnetic fields will cancel, leaving a magnetic field that points to the left on the bottom and to the right on top. So that's kind of the loop that we want to draw. The Amperian loop will go around, and we'll want to make it circulate the same way that it would for a wire. So we want to circulate our magnetic field going clockwise around that loop. Okay. And then the projection on that loop, so remember, Amperian loops are just existing in your imagination. They're kind of like Gaussian surfaces. They just allow you to do this symmetrical calculation. But we have down below with the negative z, we have the bx point in the minus x direction. So we want to stick a negative sign in front of it. And it should be constant along the path. So we'll say b times minus b times L is equal to mu naught. And we'll just say that there are n wires. We won't count them. There's 5 there, but we'll just, in general, say that there are n wires enclosed. So the enclosed current is n times I. Okay, and it's negative because we're pointing to the negative x. And so we should put a little x subscript on our magnetic field to indicate that. So finally, our Bx is minus mu naught n I over L. And we're just going to represent the number of wires per unit length as a little n. That tends to be something people do. Use little n in place of n per unit length. Upstairs in the positive z direction, our Bx is going to be positive, but it's the same loop, just going in the opposite direction. So we'll enclose the same amount of current and Bx is mu naught little n times I, but positive. So just like for a single wire, the magnetic field will switch directions from beneath the wire to above. What's different is there won't be any magnetic field wrapping around the sides, as the wires will cancel each other out.